So welcome everyone to the second of my introductory lectures on scattering amplitudes and Feynman integrals. Let's start by recalling what we covered last time. So I introduced the topic first by motivating it and giving you instances where what we will cover really relates to experiments both for colliders and for gravitational waves physics, for black hole gravitational waves from black holes. And after this, I went on just to touch base and make sure we're on the same ground and covered the basics of quantum field theory, also establishing my notations. After this, I started focusing and narrowing in more on scattering amplitudes and Feynman integrals, first by asking the questions, what are these option functions of? What are their variables? And we thought about kinematic variables, their momenta, and their momenta square, and so on, the Mandelstam invariants, and the problems that these have, the difficulties that come with them, although they are the most standard thing to write, yes, amplitudes in a Lorentz invariant fashion. Then I went on and covered also the spin dependence of the particles that we scatter, spin half, the fermions, spin 1, the gauge bosons. And when we are talking about massless particles, which I am focusing on in this set of lectures, we can straight spin for helicity. We need to pick an axis on which we project the spin, essentially, and we pick the axis of motion of the particle. And I also, of course, mentioned the fact that since we are talking about gauge particles, we have a gauge group. We also have charge under this gauge group, which is color as, yes, when the number of the gauge group is SU3. These are the usual gluons, but we can talk about SUN gluons also, gauge particles. And then I also introduced with you the spin or helicity variables that essentially are very convenient for describing both helicities and momenta. And so that's where we ended. And for today, I will continue with spin or helicity variables since we did not go through them fully. After this, I will talk about color decomposition. So mostly after I mentioned what kind of variables amplitudes depend on, I focused on how we can better express them, find better coordinates, better reference frame for them. And then I will also come to how to better describe color degrees of freedom and disentangle them from the rest. And after this, I will focus then on one particular method of calculating tree-level amplitude. So the first non-trivial order, or the classical order, let's say, with the Britto-Cachazo-Feng or BCFW, for short, BCFW, CFW recursion. I was asked about this. I am mostly focusing and basing myself and enriching, basing on the first reference I gave you last time. So this is the SageX Review, Chapter 1. And just one warning also for the next week's courses. They are not on Monday. They are on Tuesday and on Wednesday, so 2 lectures back to back. Next week, same room, same time. Just save it for your calendar. All right, any questions? Then let's come and remember what we covered about these spin or helicity variables. And essentially, we discussed that they cover both of these variables or quantum numbers of scattering amplitudes. And the benefit is that they automatically satisfy both the masslessness condition and also polarization conditions, whatever the spinors or the the polarization of gauge particles are, they automatically satisfy the condition, so they are less constrained in this respect. And then I started with the momenta of the particles being scattered. I multiplied them essentially with a 4-dimensional version, a Lorentz version of the Pauli matrices. I added the unit matrix. I wrote them as a 2x2 matrix, and I convinced you, hopefully, that the fact that these are massless, these particles, means that really this matrix is written as a product of 2 vectors, these lambda tildes and lambdas. And this is one particular realization of the fact that the Lorentz group, that the particles, describing the momentum of the particles, is essentially a product of two SL2Cs, or complexified SU2s that you know from your standard quantum mechanics course. I pointed out that this kind of relation is invariant under scaling the lambda tildes and lambda simultaneously by an opposite factor. If I multiply lambda with something, I need to divide lambda tilde with something else. So it's, let's say, many to one relation between this lambda tildes and the momentum. All clear? All right. So, and finally, yes, I told you that from, okay, using this epsilon matrix, Lerici-Vita matrices, we can lower and we can raise indices. The same we do with SUN groups. There are these Lerici-Vita invariant tensors. So this is how we lower indices. And we can also define these invariant SL2C invariant products with some particular orientation of the indices. And then as an exercise, I left you to establish that the product, so this is Pi plus Pj squared, this is the modulus and variable Sij, is just the product of angle bracket Ij square bracket Ji. Did anyone try this? Some tried. Okay, how does it work? Yes? It, it's what happens. How did you do it? Okay, just the matrix form and yes, all right. Mhm. Very good. So indeed, one can do it really index by index because everything we have defined it as such. Let me maybe quickly, for the benefit of everyone, are people interested to see how this comes about? A little bit, or? Okay. So, and I guess I don't need this. Yeah. All right. So, we have that Ij, Ji is lambda I alpha, lambda J alpha, lambda tilde J alpha dot, lambda I alpha dot. Okay. So this is just by the definitions that we have. Lambda tilde, yes. Thank you. All right. And then we can also use these lowerings and raisings of indices. So we can write this as lambda I alpha epsilon alpha beta lambda j beta, just by these formulas that I have left over there, times the same thing essentially for the other case, alpha dot, beta dot, lambda j tilde, beta dot, lambda I alpha dot tilde. Okay. So this is just using the epsilon. So there are many ways to do it. One is more symbolic. The other one is really, let's say that one can go pedestrian and really look at the components one by one and do this. And then once we write it like this, we essentially also recognize, so this lambda tilde alpha, lambda alpha is really also P alpha dot alpha, the matrix that we had. So alpha beta, P I alpha dot alpha times, hopefully, okay, yeah, P J beta dot beta. So really the same thing here. Have another lambda tilde beta, lambda tilde, but with J index. And then we can also write P uh, um, in terms of the sigma matrices. Sorry, this is P mu times P mu. So let's just replace the expression for P alpha dot alpha, multiplying P mu with the sigma matrices, and this is then yes, epsilon alpha beta, epsilon alpha dot beta dot, sigma bar alpha dot alpha mu times sigma bar beta dot beta mu P mu I dot P mu J. So all formulas we also covered, and in fact are on the blackboard. And then what we can do, if we want to be a bit more symbolic, we can collect this factor over here together, sorry, these two epsilons together with this sigma beta, let's say nu, these objects here, and then we can convince ourselves, again, this we can do index by index, so let's call this object here sigma nu alpha dot alpha, and we can convince ourselves that this is the identity matrix times sigma. So very similar to this one, but the sign has disappeared. And then if we do this, going back to our expression, so then Sij will be sigma bar alpha dot alpha, sigma nu alpha alpha dot P mu I P mu J. And then you can see that these indices, okay, these are contracted, we are summing over them. These are also contracted. So does anyone recognize what this is in terms of these matrices? Sorry? Yes, okay, that's even faster, indeed. So this thing over here, okay, the fact that we are multiplying the two indices means that we are multiplying the two matrices. Rightmost index to the firstmost index. And then the first that we are summing over these is the trace. So this is the trace of sigma, sorry, yes, of sigma bar mu, sigma bar nu, sigma nu. And this trace, indeed, by just inspecting also the form of the matrices, the Pauli matrices, this is indeed equal to 2 eta mu nu, this trace. And therefore, if you then work it out, you see this is 2 times eta mu nu P mu I, P mu J, and this is nothing but 2 times Pi dot Pj Lorentz vectors. And because we are massless, this is also Pi plus Pj squared. Just to demystify how, yes, one works with things, and this is one way. Or we could have, as also your colleague here mentioned, we could have also simply used the explicit form of these matrices and done everything like component to component. Okay, so there is nothing to mystical about these spinors, these SL2C two-component objects, and we can work with them as we do with 4 vectors and so on. And let's also interpret this relation. Let's interpret that Sij is just Ij angle times Ji bracket. We can interpret it by noticing that when when the momenta are real, then P dagger should be equal to P. You complex conjugate and you transpose, you see it from the matrix, right? So for P real, you have, and if this is to be real, this means also that lambda and lambda tilde are a complex conjugate of each other, maybe up to a sign, but this means that lambda alpha star is okay. There is a freedom of a sign, lambda alpha dot. Simply because, yes, I dagger the matrix, and it should be mapped back to itself, and therefore this the columns and the column vector and the row vector should map into each other. There's no other way. Now I'm really thinking at the level of this matrix. So I'm not particularly, you're asking how is it that I map well, it is as this equation tells you. Exactly. And if this is true, so if we are sticking to real momenta, then this means that this z can't be anything. This z needs to be restricted to be what? A phase. Very good. Yes, essentially z and 1 over z are related, so we should have z square equals 1, and therefore it is a phase. We can also consider complexified momenta, and we will, because it helps in some situations, but really this case, z, yes, is square equals 1, so this is not any complex number, it's a phase. And if this is a phase, you can think of this as really the absolute value square, the modulus square of ij. So this is essentially the modulus, it's a modulus squared. So it's in this sense that the absolute value of angle brackets or square brackets is the square root of Mandelson variables. But then you also have the phase encoded in this object. And it's this phase that describes also simultaneously the helicities of the particles. That's why we can simultaneously describe both momenta and helicities. So is the Mandelstam invariant. And a few more words about these square brackets and angle brackets. There are many identities among them. So, and this is because you already sit in this relation. Not all of them are independent. Some components are related to others. So they are themselves also not completely independent. Because, exactly, not all lambda tilde are independent. And one identity that we will use also in today's lecture is the so-called Schouten identity. We will use it, identity, which tells you that lambda 1, lambda 2 angle times lambda 3 vector alpha, or maybe I should just, if I, instead of lambda 1 and lambda 2, if I just put in this is 1, 2, is that okay for everyone? Okay. Lambda 3 plus 2, 3 lambda 1 alpha plus 3, 1 lambda 2 alpha equals 0. So if you take any three spinors, okay, this also holds for the lambda tildes, in fact, just by virtue of this relation, say, but who can think of why this is the case? Excellent, excellent. So spinors, these objects are two-dimensional. They have two components. And it's just a mere fact that you cannot have more than two vectors that are independent in two dimensions. So any three vectors in two dimensions are linearly dependent. And if you just, okay, this could be, you know, C1, C2, C3, and then if you try to solve for the system, you see that you can set these constants to these inner products, essentially. So this is really just linear dependence, 2D, linear dependence. That's all that this identity tells us. And now, this, let's say, concludes what I wanted to cover as far as the use of helicities for describing the kinematics is concerned. Let's move on. I guess it's a good time to pause briefly and see if there are any questions. Okay, let's see how they describe helicities. And for this, I already hinted this to this. It's in the phase of lambda, lambda tilde that we encode the helicity of the particle. And we can start with spin half particles, so the Dirac fermion, Dirac, and if we can use a basis for the gamma matrices, where gamma 0 has this off-diagonal form, and then the gamma i's are related to the Pauli matrices. Normally, the standard, perhaps, basis that you have seen is where gamma 0 is diagonal. But you can pick many different bases that just respect the anti-commutation relations of the gammas. And this is a particularly convenient one. And in this basis, you can show that P slash, namely P mu gamma mu, is just the matrices we've been thinking about. P dot B 0. Where these P's are the products of the lambdas and lambda tildes. So every block is 2 by 2 as the Pauli matrices. And then, are there any ideas of how we could use the spinors of the momentum spinors that I introduced in my previous? So we have that for spinors. I introduced this in my previous lecture. That P slash these U's, we can call them plus or minus or 1, 2, doesn't matter, is 0. This is the momentum version of the Dirac equation when the masses are set to 0. So if there were masses, there would be a minus m, and this comes simply by writing down the Dirac equation and then assuming a plane wave answer. So I covered this last week. So we are looking for these objects over here. Any clue of how we could pick them with respect to lambdas and lambda tildes, given that gamma, so P slash is essentially this kind of matrix. So we're looking for a four-component matrix that when multiplied by P equals 0. Yes, exactly. So I will take the liberty to add this over here, but I will not move further with moving this, with using this whiteboard. But essentially, just by these two equations, it seems that we can pick U plus to be lambda alpha 0, and then U minus to be 0 and lambda alpha tilde. Who doesn't see why this is the case? Don't be shy if you don't see it. See. Okay. So this has to do with the fact that you are multiplying this matrix, and you are multiplying, therefore, with from the left. So you have to look at these kind of products. So okay, you multiply for let's see, this line with this line for the first component, this line with this line for the second component. So as far as the first line is concerned, you see that you get 0 simply because you get 0 times something, and then something times 0. So the first component of this equation is satisfied simply because it's the product vanishes. And then over here, you multiply this P with this. Okay, in this case, you have essentially, so let's write this. The second component is lambda tilde beta dot, and then you have the product lambda lambda. It's lower index times upper index, and this object vanishes. This is antisymmetric. And similarly for the other component. So therefore, we can immediately pick, yes, also our spinors, our Dirac spinors based on these SL2C spinors. And this is how they also encode the helicity of the particle for spin half. And similarly, we can how do you know that this is the plus and this is the minus? Well, I have not said what plus and minus are. So I'm glossing over this for the moment. It has to do with positive and negative energies, and I would have to explain why the chirality of the particle, which is encoded with respect to the gamma zero matrix, is related to the helicity. So I will not spend time on this, but we can discuss it also during the break. More questions? Okay, then spin one. So this is the gluon or gauge field or gluon. And in this case, again, essentially because we have that the Lorentz group is a product of SL2, a product of two SL2Cs. We can write down also the polarization vector is a vector. We can write it as some left spinor and some right spinor, some tilted spinor and some untilted spinor, simply because it's a vector. So you have polarization vector epsilon that we discussed last time. And this I will write down how it looks and then motivate why it is the case. So we have, again, since we want to describe everything in the SL2C language, we again multiply the vector. And we mentioned there are two physical polarizations for the gauge particle, just those that are perpendicular to the direction of propagation. So we just change the indices from 4 vectors to these matrices. And then we have that epsilon alpha alpha dot is square root 2 lambda alpha xi tilde alpha dot lambda xi. And then epsilon, sorry, this is the minus, this is the plus, is again square root 2 lambda, sorry, psi alpha lambda alpha tilde dot c lambda angle bracket. Okay, so they have the general form of the 4 vector in this matrix notation in the bispinor language. But how about these x's? What do they mean? What do they come from? Any ideas? Which are not proportional to lambda and lambda tilde. If they were proportional, this object, yes, would not make sense. It would be kind of longitudinal. So, and any clues, any ideas? The fact that, yes, it's a vector, it's a Lorentz vector, so it must also be expressible as a 2 by 2 matrix in the SL2C language. And then it's a matter of what are the left and the right spinors. Very good. Excellent. These are because of gauge invariance. So essentially, these drop out. These objects drop out of final result for the amplitude. And this is indeed gauge invariance. We can show, and I will not have time to do it, but it's an exercise for students, exercise for whoever is interested. You can see the orange on the blackboard, right? It's visible. All right. So you can show that if you change xi a little bit, let's say on the plus, it doesn't matter, xi plus delta xi, then this will be an infinitesimal change in xi. Then this will be equal to 2p alpha alpha dot delta xi times xi divided by xi lambda squared. Okay, let me put it as leftmost as possible. I guess this, I cannot move this. So plus square root 2 lambda alpha, sorry, p alpha alpha dot times delta xi xi angle bracket xi lambda squared. And to show this, you have to essentially differentiate with respect to xi. Differentiate this formula over here with respect to xi. There will be dependence on the denominator and on the numerator. Sorry, here. And then we will also need to use the Schouten identity for some simplifications to get to this result. But based on this, you can also show, so from this equation, let's make it the square equation. Then from the square equation, you can also show that P dot E plus minus xi, where okay. P is the momentum of the particle and is related to lambda tilde lambda, as we have written there. So this is the polarization of the particle with this particular momentum. Then this thing is equal to zero. Okay, this has to do with the polarization itself. But in fact, what you, okay, this you don't even need this relation. It's the fact that this is also equal. This equation remains unchanged also, sorry. If you change xi plus delta xi. So it's the fact that you transform your polarization vector, essentially, to say it in words. These x's transform the polarization vector with a component that is parallel to the direction of motion. And therefore, by gauge invariance, by the fact that we are talking about polarizations that are physical ones that are perpendicular to the direction of propagation, this is just another gauge, another choice of gauge for your, yes, gauge theory. So, and then who will tell me how about the remaining factors? Okay, this more or less explains why we have this lambda xc combinations. How about the denominators? Uh, Uh, one could see how this translates, but there are other simpler conditions. So these vectors, we chose them last time to be of what norm, of what size, absolute norm. Yeah, these vectors. When you describe the polarization, does the norm of the vector matter? No. So yes, last time we indeed specified these to be, because we care just about the direction. Let's see, I guess. We showed or we discussed that E uh, squared, E plus minus squared equals, sorry, 1 uh, E plus equals 0, E plus dot E minus equals minus 1. And this is equivalent to saying that E1, sorry, E1 squared equals E2 squared equals 1. So this plus and minus had to do with picking E1, so usual linear polarization vectors, and taking the combinations. So E plus minus, where E1, I guess I had the indices down last time. 1, 2, plus minus I epsilon 2. So just from these equations and these like change basis, you can arrive at these relations. And essentially, these are normalizations so that the vectors, okay, this is independent of normalization. You can see it by plugging in, taking the product. This normalization has to do with the extra denominator here, just to motivate these formulas, which don't look particularly intuitive once you first look at them. All right, so this completes our discussion of spinor and helicities. I know it was a little dry and technical now at the end, but it's just so that you get a sense, even if you, okay, you really, if one is interested, one has to simply get acquainted and try to calculate a few things with these conventions, this formalism. It's really called the formalism, spinor-helistic formalism. So it's a matter of getting acquainted with calculating things this way. But we will, yes, some of the basic concepts we will need when we are doing BCFW, so that's why it was necessary to at least have some exposure, having seen these things. And it's a good time to pause and ask if you would like to some clarification on spinor helicities. Otherwise, we switch gears and go to color decomposition. Okay, it must have been brilliantly clear then what I was saying. But let's see. Let me erase here. Or is it okay if I erase the full thing? Just to start on a clean slate? Okay. Let's at least introduce color decomposition before the break, and then we go on. Okay. So one, is this visible on this blackboard? The blue? Good. So after describing what are the variables of the scattering amplitude, I try to explain one possible way to simplify kinematics and helicity information. And now we'll go on and see how we can also simplify life with color degrees of freedom. And for simplicity, we will restrict to pure gauge theory, SUN gauge theory. So no fermions. So these are the gluons. So yeah, no fermions equals quarks. We will just have the gauge particles named the gluons. And from what we have discussed so far, we know that the amplitude, let's say the n particle amplitude, is now defined as momenta, helicity, and also color, which are these are adjoint color indices. Namely, they run, so alpha I goes from 1 to n squared minus 1. So for SU3, there are 8 types of gluons. So these are, yes, adjoint indices. The gluons are in the adjoint representation. And we already discussed, indeed, that we can more compactly, efficiently describe momentum and helicity in terms of spin or helicity. And then what color decomposition does, and we will see this now, is that it disentangles these from amplitude. It allows us to, let's say, factor out this piece of information and then be left with some simpler building block, which is independent of color. And that's the essence, that's the reason why we are now focusing on color decomposition. So, any preliminary thoughts or questions before I move into to describe how we do it? All right. So, the first thing we do, okay, let's denote the generators of the fundamental rep of SUN as T, A, I, J, which are Hermitian and traceless matrices. Of what dimension? N by N, exactly. So I and J go from 1 to N. So if we are talking about the special and unitary group, then the generator has to be Hermitian and traceless because of the special. condition, this because of the unitary condition. All right, so just to set up our notations and convention. Then, in terms of these generators, the commutation relations, I also referred to them last time. Read TC, where this normalization, okay, we could have chosen this otherwise, but it's one choice one can make. And these are the structure constants. This is how all groups are expressed, the commutation relations of all group generators of any group, any Lie group. And then this is yet another choice we will make. We will choose, we can pick, it's a linear space, we can pick any base we like. So we pick a base such that we pick the generator such that the trace of TA and TB is delta AB. Who remembers why we are allowed to do this choice? Some group theory courses you might have taken. Sorry? Not quite. This is, let's say, the fact that we can do this. Let's say, does anyone recall more or less what this left-hand side is as a quantity? This, yes? Very good, indeed. And in the language of groups, this is called also Spartan killing form. So every Lie group, it can be proven that indeed possesses this type of linear product. Very good, and we can. Well, the theorem about Lie groups is that this trace is always an invertible matrix in terms of A and B. So essentially, we have a complete basis. And then, since it's an invertible matrix, we can choose it to be the identity. That's all that this thing is saying. So no mystery here either. Just some group theory. So, and then, questions? Why it is that it's essentially the statement that the generators form a complete basis for your group as a local, yes, all local, yes, changes of your group elements. If you generalize Lie groups to, I don't know, affine groups and so on, then the whole structure is not as straightforward. So this pertains to all Lie groups. With your structure, do you need an I in front of that to make the condition? The I over here? Yeah. Yes. Mm-hmm. Yes, yes. Mm-hmm. Indeed, you have the eyes, the number of eyes matches, yes. All right. So then, from the previous steps, from steps 2 and 3 above, you can also show that F, A, B, C, let me write more leftwards. So F, A, B, C equals minus I over square root 2 trace TA and then commutator TB, TC. Does anyone see this? How do you go from here and here to here? Exactly. Just multiply this with, I don't know, TC. Okay, maybe you need to relabel the indices a little bit, but you multiply this with TC, sorry, TE, yes, TF, here and here, and then you take the trace. The trace will then make the right-hand side be TF, whatever matrix you multiply it with, and you arrive at this formula. So it's as simple as really multiplying and taking the trace. And okay, also write this as trace TA TB minus trace TA TC And even though, okay, from this it's clear that what happens if you exchange B and C? You get a minus sign. What happens if you exchange A and B? Yes. So in fact, it's fully antisymmetric. But to show this, you need to also use the cyclicity of the trace. Trace ABC equals trace BCA, and so on. And you see that, so essentially, these structure constants don't have to be fully antisymmetric, but you are choosing, let's say, you are doing a good quote-unquote choice, where these structure constants are fully antisymmetric. And so they don't include any kind of, yes, uh, unnecessary information. All right, and uh, then the next step is that also, okay, for any, sorry, we use the fact that any Hermitian matrix equals the product of, let's say, C0, the unit matrix with some normalization, and all the generators of SUN. The fact that I also added this is because I'm going from SUN to UN, all right? So I also need to eliminate the tracelessness condition, let's say, and so I can add the generator. So if you add the generator to SUN, the unit matrix, it becomes UN. And so any unitary matrix, as I can express as these generators over here. And then this tells you simply that you have a complete basis. So it's a completeness relation. So complete basis for your Hermitian matrices. And from this, you can also deduce that TA I1 J1, TA I2 J2 equals delta I1 J2 delta I2 J1 minus N. I switch the indices. I1 J1 delta I2 J2. Yes, indeed. So I use the Einstein convention where repeated indices are Yes, sound, yes. T's? It did, yes, like just like Pauli matrices. Here. Uh, well, if mhm. This is the standard convention in all the books I've seen. Uh, well, if it's you can choose them. Yes, you can. Yes, yes. So this is the last thing I'll say before the break. I know it was a lot of yes technicalities, but just the last comment, and then we resume. So, but if you are thinking about for pure gluon amplitudes, pure gluon amplitudes, can in fact can drop second term. So let me use, I don't know, this color. And the reason why I can drop this is that, okay, I named this extra generator T0. So this is essentially T0. This, so this is, I added one generator to make SUN UN. And this, this is the identity. The structure constant of this generator, 0 BC is 0. Essentially, what do you do? When you make an SUN gauge theory to a UN gauge theory, you add a UN gauge field. So it's a photon. It's a photon, like, yes, uh, a, a quantum of electromagnetic radiation. And photons just scatter through everything. So photons don't interact with themselves. So this is what this formula tells you, and therefore essentially um, uh, uh, the interaction vertices of SUN theory and SUN theory are the same. So SUN and UN uh, gauge theory. Sorry, yeah, I'm running out of space. Vertices are the same. You don't have, yeah, if you have an additional uh, like photon, which simply doesn't talk to anybody else. So you can, if you were in an SUN, so in UN theory, you would not have this piece and you can neglect it. That's okay. The gist is that you can simplify your life and really think of this formula just having the first step, so to speak. All right, so it's a good time to take a break. I apologize if this was a bit more technical this time, but it will get better, I promise you, in the next half. More or less, yes, the technical part is over, and we will start also BCFW after I finish with this, which is, yeah, maybe another blackboard of this size, and then we move on to BCFW. So do stick around for the second half. Thanks. In 5 minutes, say. Okay, let's try to close this chapter on then color decomposition so that we can understand, yes, then we can move on to maybe some more interesting stuff or some cooler stuff. So the next step, if this is V, then this is VI, okay. So we have to think about Feynman diagrams. How does color enter? Color is through the vertices. I also mentioned this last time. So we have A, B, C, and this is proportional to FABC. And then this is also, I didn't write this last times, but similarly the 4-point vertex, A, B, C, D. So these are really just the non-linear terms in the gauge field Lagrangian. And because you have that the fields are matrices and you can expand them in terms of the generators, you find C, D, E. Okay, so maybe this is not visible. Let me put it on the second line. So F, C, D, E. C, D, E. So two structure constants, and we sum over one of the indices. Yes? Here. It covers. Okay, sorry, yes, I wanted to save space, but let me write this on the left. So, okay, so this is proportional. This is proportional to F A B E times F C D C D E. And we are adding, we are summing over E. All right. So essentially, we think that we start and we have our Lagrangian and we start to sum over all terms and see how we can package things nicely together to disentangle all the degrees of freedom. So the step one is that you use the relation of step 4, this one over here, in order to trade F's with products of traces. So we have trace TA dot dot dot, I don't know, some TD times trace TB dot 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 TD, and hopefully it's clear that these indices A and B that are open correspond to the external particles that we have in process, the gluons that we are scattering. Open indices are the external particles. Whereas those that are repeated indices or contracted or some indices, contracted indices, these are the internal gluons or the vertices. Just like this vertex over here, we are summing over, yes? Yes, very good, indeed. So all I'm saying is that wherever you see an F, if you take your sum over Feynman diagrams, you replace it with this formula over here, and you can therefore get a product of traces, a sum of products of traces. Cool? All right. The step 2 is then, let's see, where should I write? Step 2 The step 2 is to use then this relation 5 to eliminate contracted indices, contractions, or in other words, to merge traces. So if you see this written, probably this looks kind of funny to you, or it's not immediately visible, but let's be explicit what I mean by this. And let's consider this example. Okay. Trace TA, TB, TE. So this is related to essentially this vertex over here. It's part of this, not the whole thing. Trace TC, TD, TE. Now, I can give you the final result and then work it out. I can work it out and lead you to the final result. I can just quote the final result. What do you want? Who wants to see the derivation? Just one hand. So who doesn't want to see the derivation? More hands. Okay, so let's keep it. So, but with these formulas, you essentially get that this becomes trace TA, TB, TC. What did I do? I eliminated, so there was T on the left-hand side, T on the right-hand side is product of traces. Essentially what happens is that you merge the two traces and you kill this extra generator. Go ahead. TD, sorry, yes, thank you. TD, yes, it survives. So this, okay, you have to play around with this formula. Just you have it inside the traces. You know that the trace means summing over, yes, the two indices of the matrix. So it really is an application of this formula with just this term. We are thinking about just gluons. So this equation, if you plug it in here, has this result. So this is an exercise for students. Exercise for you. What did I use this color? But it doesn't show you. Okay. So in the end, so after the dust settles, what we end up with, essentially we eliminate all contracted indices when we do this. So and it turns out that in the end, you have that the maximum number of trace products equal to, does anyone, okay, what could it depend on? What kind of data of your Feynman diagram could it depend on? Sorry? That's one variable of your scattering amplitude. Any other guesses? Loops. Good, indeed. Because there will always depend, this will always depend on the external particles, no doubt. But the question is how many products thereof we have. And it turns out that this is equal to loop order, let's call it L, plus 1. So, or at least I should say, it looks like it up to 3 loops. I'm not personally aware of anywhere it being proven, but let's say, let's specialize the 3 level because this is what we are starting to think about. So restrict to 3 level or L equals 0. And in this case, you have the following quite beautiful formula, I believe. So this is our scattering amplitude, I denote it with a cal k, a cal I. So it depends on all these variables that we talked about. And this is a sum that is a trace, a single trace in this case. And we have some generators which I denote as T sigma 1 all the way up to T sigma n times what I have as a regular A, 0. Let's call this sigma 1 up to sigma n. Let me put also a box on this equation. And I should also say that this is, okay, what are we summing over? Sigma belongs to the permutation group of n, modded out by Zn. So, okay, we have one trace, and we are summing over all non-cyclic permutations. So Sn, where you mod out by Zn, are all non-cyclic permutations, which are equal also to Sn minus 1, because you just fix one leg, and permute the rest. So since essentially the trace is itself cyclic, if you have, as I said, TABC is equal to TCBA, so you don't need to consider this transformation because the trace is already invariant under this. So you permute all the remaining, so sigmas are permutations, 1 goes to 2, 2 goes to 3, all possible permutations. And the permutation sigma has sigma 1 up to sigma n, meaning where does the first element go to the third, the fourth, and so on. So these are the permutations. And then you have that this object A and 0 is the color ordered. So it's the color ordered amplitude. And it is independent of the color indices. We have completely factored out all color information. It only depends on the momenta and the helicities. And so it is also simpler as a function, and I will explain what I mean. And it's also individually gauge invariant. So essentially, at least at tree level, and okay, the story goes on similarly at loop level, we can forget about the object we started with, and then focus on the color order amplitude. I guess I forgot to mention one last thing, that then sigma I, where I call over here sigma I mean I am also permuting the labels of the particles. And hopefully you are familiar with notations or permutations. Sigma as a whole means, I don't know, 1 goes to 3, 3 goes to 5, and so on. And so each of the n elements you permute of a single permutation is called this S parenthesis I. So S1 means that in this particular permutation, element 1 goes to element 5, for example. And also, as far as my statement that this is simpler, what does simpler mean? It means that that these color order amplitudes has poles only when adjacent momenta pi plus 1, pi plus k square go to 0. So this is, okay, the fact that amplitudes might become singular where some momenta, in this case, vanish, some momenta square vanish, is just a statement that you have propagators. Feynman graphs consist of internal lines, which are propagators, 1 over p squared. And if it happens that one of the internal particles goes on shell, you will have that this propagator becomes singular. And while for a general scattering amplitude, you could have, let's say, any combination of momenta to that becomes singular would be a pole, would be singularity. Only a subset of these occurs for color ordered amplitudes. So this is all I had to say about color ordering, and now you are really completely set to understand the simple equation I quoted first in my previous lecture, the so-called Park-Taylor formula, because it's really on the left-hand side a color-ordered amplitude that goes on the left. That's why it had no color information on it, no color indices, just these spinor brackets. And exactly, the right-hand side had some very compact ratio of spinor brackets. So it's a time to pause and see if there are questions about color ordering. The nutshell, the gist is that doing this careful decomposition of color, in the end, you factor everything out and you care about one object. And notice, this just needs permuting. You get the full amplitude by permuting this object. They're changing the labels. So one size fits all, at least at 3 levels. You have reduced the multiplicity. Instead of having to compute every different trace coefficient, you really compute one and you get all the rest from permutations. And you can even write down color ordered, so-called Feynman rules for this object, which are simpler from the ones you started with. Just get rid of color from the Feynman rules altogether. The fact that you have particle I plus 1, particle I plus 2, sorry, yes, I mean there is a cyclic ordering, yes, of the external momentum. Thanks for your question. Any more? I raise? Okay. So I have left some exercises, or yes, for you to do some calculations that might be helpful in you to yes, in convincing yourselves that the procedure I described works. But if you, yes, or essentially, yes, the punchline, or if let's say the key message that you need to keep from what we covered so far, when we move to more cool stuff. So this is 3 level methods. BCFW recursion. The key information to keep is that we can encode helicities and momenta with momentum, with spinors, with these lambdas and lambda tildes and their spinor products, and that we don't need to care about color. We can have factored out color. We are now only considering color ordered amplitudes. And this is where this recursion comes in. This is what this recursion describes, color ordered amplitudes. So in the 1960s, there was the strong belief and hope that amplitudes are determined from their analytic properties. And in order to, this was a whole S matrix program that also then gave birth to many interesting developments, including the conformal bootstrap today. And being inspired by this thesis, this belief, basically physicists study the amplitudes as functions of complexified Mandelstam invariants, complexified momenta. But since the number of Mandelstam invariants, as we discussed, grows very fast with the number of particles, so you have complex analysis with many variables, this was extremely hard. And there's a book also called Failed Causes in physics, and it includes also the the S matrix program. Even though it really inspired many other developments, itself, it's fair to say that it was not very successful. But one of, let's say, the ideas that it gave birth to is this BCFW. So instead, the gist of it is that BCFW recursion it does what? It maps singularities and when I say analytic extraction for any function, essentially, where is it singular? That's the main question that, analytic structure relates to. So map singularities of the color ordered amplitude, AN0, which I now, again, I drop P and S, I just refer to the particles by their index. So two poles of a single complex variable. So variable. So instead of doing complex analysis in many variables, which is extremely hard, BCF initially, joined by Witten later, they thought that they realized that one can consider a simplified setting where one complexifies just one variable. And let's do this. So let's introduce a deformation. Okay. So introduce of two adjacent legs, one and n, as follows. I take the lambda of 1 and I replace it with lambda 1 hat of z, so this is the variable we are talking about, which is L1 minus z lambda n. And let's do the same, and whereas lambda n tilde, lambda n 1 tilde is unchanged, remains lambda 1 tilde. So I just change lambda without changing lambda tilde of particle 1. And I also take particle n, and then lambda of particle n remains unchanged, but I deform lambda tilde. So I introduce this variable z through this deformation, lambda n plus z lambda 1 tilde. So now I have introduced this z variable in the game. And from the relating lambdas to p's to the momenta, it's not hard to show that P1 now becomes lambda 1 alpha dot lambda 1 minus z lambda n alpha. And similarly, Pn alpha dot alpha is the same, but with a different sign. Well, also lambda tildes and lambdas get exchanged. So lambda tilde n plus z lambda tilde 1 alpha dot alpha. Okay, so from the spinors to the momenta, and there should be a lambda alpha here that I forgot, sorry. Lambda alpha. Here is a tilde, here is a tilde, so where? Here is tilde, here is tilde. Here? So the lambda n of z tilde, yes. Lambda n till lambda no, this is lambda. This is lambda, this is lambda tilde. This is lambda, this is lambda tilde. Hat. That's what you meant. Yes. Well, this is, yes, indeed. This hat. That's what you meant. Yes. Very good. Thank you. So lambda n goes to lambda n hat. Yes. Thank you. That's what you meant. Lambda n tilde goes to lambda n tilde hat. Indeed. Okay. So who could tell me what happens to the sum of P1 hat and P2 hat? So this, I guess, let's see. Did I put hats here? No. Let's do that too. Hat. So what is the sum of P1 hat plus P and hat? Exactly. So momentum conservation is unchanged. And then how about P1 hat squared? What's that? Yes, very good. And similarly for Pn hat squared. So it's a deformation, it's a very special deformation because also masslessness is unchanged. So in fact we have that An, the color order amplitude of Z, which we can also denote as An of 1 hat, just for simplicity, 2 and hat, is a one parameter, is a one parameter family. Of amplitudes. We have, yes, deformed our amplitudes, but respected some of its very basic conditions. And then we can ask ourselves, what are the analytic properties? Of An of Z. So I will finish in 15 minutes, if that's okay with you. From thinking about Feynman diagrams. So this is 3-level, we are summing over 3-level Feynman diagrams. Yes, yes, indeed, even if you, yes, think about the original amplitude, and yes, you're asking about, yes, the properties with respect to Z in particular, that's even more tied to, indeed, more relevant for BCFW. But in general, yes, so indeed, with respect to Z, you are right. We have simple poles in this multi-particle channels, where in this case adjacent momenta go to 0. So capital P I hat squared equals little p1 hat plus p2 plus pi minus 1 squared. And this I can also, is it okay if I raise here? So you recall that, okay, we have shifted the lambdas and lambda tildes, one of each, for particle 1 and particle n. This is a statement that I mentioned earlier to you for any multi-particle channel. So, okay, now we are in particular interested in the Z variable. That's why we are considering only this subset. So when this thing equals 0. And this you can think of like from Feynman diagrams. So you can understand from Feynman diagrams that if you have an an of z, and you have so I minus 1, I dot dot dot, n minus 1, n hat, 1, 2, dot dot dot, and so on. So this is okay. For finite diagrams, we remember that we have propagators I over some big P squared. So we just, in any diagram, you will have the external legs being connected by some internal propagator to some other external legs for any three-level graph. And it can be that this propagator, so this will be, since it's a three-level graph, there are no loops, it will really be a sum of external momenta at tree level. And it can happen that the external momenta align themselves such that this thing vanishes. And this is where the tree level amplitude has some singularity. And then you can see that, okay, if you analyze this diagram by diagram, you will see that in fact diagrams factorize. Different diagrams share the same internal propagator. So let's have them all outgoing. It doesn't matter, but it will. So times 1 over p squared, in this case pi hat squared, times, okay, I need to go a bit to the right, forgive. So this is 1 hat, 2, and so on. Let's say up to I minus 1. This is I plus 1 all the way to n hat. A right. Okay, now that I drew it, I don't know, we can think of the direction being going from right to left in this setting. So essentially, if a Feynman graph, three-level Feynman diagram contains the propagator 1 over pi squared, then there might be values either of external kinematics of z where this thing vanishes. And what one needs to experiment and see from Feynman, so it's not hard to see that the three-level Feynman diagram and therefore the amplitude itself will have a pole, simple pole, because of the propagator when this momentum goes to 0. What is slightly more non-trivial is that in fact the amplitude factorizes. So let's say if you sum over all Feynman diagrams that share the same propagator that goes to 0, their sum has a factorized form into a left amplitude, let's say right amplitude, and then this pole, this p square equals 0 pole. And especially with respect to z, so this is the variable of interest, this is the variable we added. We can see that we can have how many simple poles in the variable z. Suppose I fix the momenta, I don't move them, and then I move this z around. How many poles, possible poles, will we have? 2, which corresponds to the internal particles. Well, this is about p squared, so it's not tied to the helicities per se. Helicity has to do with the left and right amplitudes. But where are the poles of p squared equal to? What's that? Momentum is conserved, but let's say, what is this? Okay, what values can this I take? From 1 to n, let's say, very good. In fact, from 3, because you need, let's say, to have at least 2 legs of each of the amplitudes left and right. Otherwise, it's not a scattering, so to speak. So you have indeed n minus 3 in total poles in Z. And these are exactly when I over pi hat squared. Can people see when I write here? Okay. Is equal to, okay, we write this down and then explain. It's pi squared without hat minus z n pi 1 equal, I have to keep going now, there's no going back. In the end, we as humans expand in all the possible space we get, unfortunately. But okay, what have I done here? I have, first of all, okay, I have essentially replaced the big P with the little p's, and then also it's with respect to the lambdas and lambda tildes. And this object over here is defined as n pi 1 is lambda alpha n I alpha dot lambda tilde 1 alpha. So, and the I, indeed, okay, CPI squared. Okay, let's try to unpack the information. Okay, I belongs to 3 to n minus 1. So maybe for the sake of people in the audience, sorry, for those who want to attend this also online, I should try to, okay, it's even visible. Very good in the video. All right. So the point here is that I can take values from 3 to n minus 1, because either from the left or on the right-hand side, I need to have at least 2 legs. This is the this I over here. So this gives you a total of n minus 3 poles. And then what I can do is I can replace this big hat P with the expressions that we derived from P hat 1 and P n hat. And because of the special way that uh, I have deformed my momenta, this propagator becomes a linear function of z, just a linear function of z. And the coefficient comes, okay, from the terms that we added z on, they multiply this p from left and right. And this is how I, yes, denote these combinations of lambdas and p's of contracted indices. And this is alpha, this alpha dot. And then, okay, going from here to here is just a matter of factoring this coefficient so that I have something that goes like z minus yes, has coefficient 1 around z. So this is just this final equation where, yes, I basically divided by this factor, and here I only have pi without a hat. So this is really the momenta of the particles. All right. Then let me write down the final formula, and I will have to explain it to you the steps more next time. But after I write it down, we are done for today, and thank you for your patience. Okay, so our goal is to obtain our original. After all this gymnastics, what do we want? In the end, we really want an when z equals 0. This is just a way to exploit analyticity, but this is how we want to do it, and we do this from Cauchy's residue theorem. We have that indeed an equals an at z equals 0 of the deformed amplitude to be equal to the 1 over 2 pi I, the residue around 0, dz over z an of z, where this is really a small circle. So if this is the z plane, complex plane, this is 0, and we take a small positively oriented curve around 0, very small, where the poles, you know, ZP1, ZP2, lie outside. Some very, very small circle around 0. And then, okay, this is a linear, sorry, this has a 1 over z minus something denominator, but at z it is well defined, are complexified, are deformed amplitude. So therefore, I just pick up the z equals 0 contribution, right? Now the whole thing, the whole trick here is that I can expand, let's say, my circle, and every time I expand my circle, I add also residues on around these poles on the left-hand side. This is the integral. It will not just be this bit, it will be also the poles at ZP1, ZP2, and so on. So if I bring them on the other side, so if I take and expand this circle all the way to infinity, then in the end, I will get, so equals I equals 3 to n minus 1. This is the final formula for today. Some where the helicities are indeed plus minus. And then I have a I 1 hat 2 dot 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 minus big P I. I guess I should have also, yes, of minus helicity here. And then times I over P I squared. P, sorry. And then A n plus 2 minus I. P I now with plus helicity. What is it? I. Sorry. N minus 1 n hat. I really just evaluated, okay, it's a lot of formulas. We can come back to it next time. We will start from here. I just expanded this little circle. This bit we understood just by residue theorem. I expand the circle, I pick up the residues in all possible poles, all possible poles of this function. It could also have a pole at infinity, but in the end we will see that this is 0. I will have to come back to this next time. But once you have to take my word for it that this also residue at infinity is 0, then this formula, this simple complex analysis massage of the formula allows me to write the n particle amplitude as a product of particles with the lower length in the end. And so this is the BCFW formula. It was originally written by BCF without, just by, well, they had some motivation, but they could not prove it, and then Witten got interested, and then all together the four of them proved by this simple complex analysis argument that yes, this is the right formula and this residue is 0. But it is constructive, so it is constructive. If you know the n particle amplitude, you can get the n plus 1 particle amplitude. Just by analytic structure, okay, and some general yes, properties of how amplitudes behave, which stem from Feynman integrals, but in the end, we did not sum the Feynman diagrams. We just used some general properties, some analytic properties, and we arrived on a recursive formula for writing them down. Thank you very much for your patience. You're welcome to ask questions as long as you like, privately or now in public, and yeah, let's go for pizza.